Hello, everyone. Thanks for joining. This is Gleb from SatRevolution. I'm here with my colleagues Tomasz Pozniak and Grzegorz Mazec, and we're starting the next session on building an agile constellation, SatRevolution REC. So this is the week of the SmallSat 2020 that's happening online. And there are over 300 participants there, and most of them are putting online content out. So we are very honored and happy that you have selected us and our webinar and joined here. So thank you for that. We hope you will find it interesting and useful. Please feel free to ask questions either right away or at the end of the session. And with that, we will begin. Also for consent purposes, we are recording this session for future content on our website. So just to keep that in mind. So next slide is about us. Some of you may have seen it already in the previous webinars. SatRevolution was founded in 2016. We've launched our first two CubeSats last year in 2019 from International Space Station. One of them was our proof of concept satellite, Retovid, with an in-house made optical payload. We're currently working on a number of dedicated and shared missions for our customers. And then hopefully by the end of this year, we will have a total of 7 CubeSats in orbit. We're planning a number of shared missions for next year, which we've announced and will announce later today. They're called Stork and SOA, the 3U and 6U shared platforms with optical payloads. So please check out our announcements and also our website. And of course, the big goal at this stage for us is to launch our first stage of the constellation in 2023, which will consist of 8 6U satellites of our constellation. So with this, I'd like to pass over to my colleague Tomasz Pozniak. So Tomek, go ahead.
Good morning, guys. It's morning in Poland and maybe evening for you somewhere else in the world. Anyway, it's good to speak to you, and I wanted to introduce the REC constellations progress and the whole idea behind the project. So I would start from the customer needs, because these are mostly the things which brought us and pushed us into the development of the REC constellation. So these were the factors. Most of them drives us into the idea which I want to introduce in a second. So basically, the first thing is specified there as a high resolution images, which is still a very important thing. Besides the whole EO business and data provision is starting to focus more on basically delivering the data about some kind of actions on the Earth, rather than just brutally handling this high volume, high resolution images. But still high resolution images are in price. Then you have another aspects like the lower services costs without reducing image quality, speed of data transfer, onboard data analysis, updates, and developing onboard intelligence, onboard artificial intelligence in satellite systems. Also, the weather conditions are, let's say, a bad factor for the customers we need to overcome. So the whole idea behind the REC constellation was just to miniaturize satellite while sustaining the comparable efficiency. So on the right side, you have the SkySat, which weighs around 120 kilograms, costs around $5 million. And on the left side, you have our ScopeSat, which is going to, which mass is going to be around 10 kilograms, and the costs around 500,000 US dollars. So what you're looking at right now is basically shrinking of a satellite, while sustaining the comparable efficiency in provision of imagery. The whole trick behind it is to use deployable optics, which is the kind of holy grail of the whole Earth observation. So we're planning at the first stage to launch 8 of these kind of satellites called ScopeSat. So that's the first iteration of the constellation, and then increase the batches per around 50 satellites, one after another, to create a real-time Earth observation constellation, because that's what acronym REC stands for. And this constellation will contain around 1,000 of satellites totally. So what ScopeSat is built, what are its parts? So there is the platform and the instrument, obviously. So the platform is called Nanobus, and that's the left side of the picture, where you can see the 3 unit volume for payload service for communication subsystems with antennas. So we're planning to implement there both S and X bands, S-band transceiver and the X-band transmitter for downlinking the imagery. So you can see the patch antennas pointed at nadir on the picture there. Of course, in the bus there will be like the power system and the batteries, and the whole ADCS with the proper sensors, actuators, and one of these actuators is a thrusters. So from the point of sensors, the star trackers there, and the IMU. So also the Earth sensor. So we're planning to use all of these sensing capabilities to point precisely into Earth surface, and actuate it with both magnet torquers, reaction wheels, and the thruster to sustain on the proper orbit for around 3 years with a satellite. So there is also a chassis and solar array deployment mechanisms, which you can easily see on the left side. And basically that's what Nanobus is composed of. And there is another part of a satellite, an instrument called Diploscope, also with a volume of 3U. So it contains an optical mirrors and baffles, milled precisely using diamond turning technology with aluminum, and deployable mechanisms for all of these mirrors to keep them together and deploy them, obviously. The mechanical structure and the camera with CMOS sensors on board with time delay integration. And as well the control electronics, because all of the instrument will be working in the kind of loop where the image detection is I mean the whole detection system will be based on the image processing algorithms. So that's what ScopeSat is composed of. So the key innovation, as I previously mentioned, this scheme about shrinking the satellite while sustaining the comparable efficiency is mostly due to the deployableness of the telescope, right? So the key innovation here is the modular diploscope with segmented aperture. And the major reductions are basically described by the numbers of mass reduction from 120 kilograms to around 10, and improved spatial resolution of imaging for a 6-unit CubeSat from 4 meters, which is, around 4 meters, could be 3 or 5, to below 1 meter. So that's our key innovation and my major reductions in the REC project. So let's get for a moment into the optical design, which we won't get deeply into. I would like to touch on the most interesting things up there. So we've decided to get into the Fizeau segmented aperture with our optical design, rather than, for example, Michelson's, and that's why that's what design we're building. So it basically is composed of the primary mirror, which is segmented, and it brings the light into the secondary mirrors and into the next mirrors, where most of them are basically without optical power. So they are only bending the light to increase the optical path, which is a cost of increasing of the focal length, which brings the instrument look in a shorter field of view, and bring the more of GSD there. So the most important thing about the optical analysis and about the optical design wasn't this obvious in the process, because there are questions from the audience.
We can address that just in a second.
Okay. So about the optical about the MTF analysis, it was the thing we've done as one of the first things in the optical design. So it isn't quite logical, but the best contrast which is detectable by the instrument, it's brought by an instrument which have 3 or 5 or more petals rather than 4. So what we thought in the beginning is just to build the petal structure on top of the CubeSat structure, right? So the CubeSat structure is based on the square. So we thought to establish the 4 petals, like the 4 sides of a square section, right? And it came out that the symmetry of such solution is not the best way of providing an image which is full of contrast. So what you see up there on the pictures is this greenish hue, which can be detected as the best one on the 3 petals image, and it shows that the MTF, which is so-called basically parameter of the contrast, is the best at the 3 petals, right? It's also fine in the 5 and 6 petals, and it could be followed there, but we have decided to stay on the free petals because this is the less complicated structure, and you know, in the satellite systems you have to be let's call it robust. So
You want to take the questions now?
okay.
One question is regarding the ADCS of ScopeSat. Is there only one fixed thruster?
Yes, there is only one fixed thruster, and this thruster is basically to station keeping purposes rather than maneuvers or orbit changes. This as we will be relatively low on around 350 kilometers, we need to just sustain there, and that's what for the thruster is on board. So I hope that's an answer for the question. And the focal length is at the current stage 1,100 millimeters, but we're working on increasing it in the final stage of an instrument. So I hope that's also an answer for Maciej up there. So we can get to the next slide. The mechanical design in its early concept it's shown this way. The most important thing that it fits into 2U structure. So you're seeing there the primary mirrors, 3 segments of them, and the 3 segments of the secondary mirrors on the piezoelectric stages. In the nadir pointed side on top of this red mechanical structure, and a couple of the tertiary mirror which still have the optical power, and then another 4 mirrors which are just bending the optical path. So they are flats mostly. And the actuating mechanism, it's basically on those 3 rods, but that's going to be adapted into better mechanical design. So that's just a scheme of how it's going to look like, more or less, right? Can we get to the next slide? So what you have seen before was the mechanical design of an instrument which is going to be flown after adaptations. But what you're looking at now is the proof of concept for the lab bench purposes. So we're at this stage currently. So we're building this this proof of concept. Let's call it a version, laboratory version, which is a proof of how really the tolerances and how the mirrors are opening wrong. What really it causes in the image damage. So that proof of concept will prove us if the calculations about the possible tolerances of the optical system is bringing a failure or not to after uneven deployment of these primary mirrors, right, on orbit. So that's how it's going to look like on the optical bench. And from this point, we will get to creation and manufacturing of the instrument, like the flight model of an instrument. So regarding the components on the platform, there is, as I mentioned, S-band transceiver and X-band transmitter. The first one for telecom and tracking, and the second one for data downlink. So you have the approximate carrier frequencies and the bandwidths with the maximum bit rates for both of these systems, and they are both on ITU licensing APA phase. For the purposes of the simulations, because we have done couple of simulations until now regarding mostly the coverage and communications, we have established some initial parameters which we stick to. So that was the design process also about how these satellites will be, separated, distributed, and how they are going to basically travel on orbit. So we've established these simple scenario parameters, and they are mostly aimed at the Polish territory. So this inclination of 54.6 is the around the maximum latitude of Poland. So, and 350 kilometers, it's an orbit which still gives us the opportunity to bring this below 1 GSD imagery and sustain a proper amount of time on orbit, so around 3 years. So this, what you see, is the kind of trade-offs to which we get to. So the ground station scenario is mostly described on this picture. So we're focusing on a couple of ground stations at this moment, and in this configuration of 5 ground stations, after simulations, we decided that we will be able to basically cover the Polish territory, one swipe over it, right, with a push broom technique, and then downlink the whole imagery on no more than 1 orbit more. So that's what the ground station and communication calculations have brought us to. Of course, this is not fixed, as you may know. We're in the development process. It's an R&D project, so these are the well, let's call them assumptions right now.
We have another question.
Okay.
How is the attitude control performed?
Did you consider using repeat orbits?
I think that's the second question.
Okay. So Alexander, could you expand your question about the attitude control? Because I'm not fully sure what you mean.
Okay, so my question is, because you have just one fixed thruster, and how do you perform the attitude control, whether like pointing of the antenna, for example, how do you control that?
Is it attitude or altitude? Okay, attitude. So the attitude control is performed this way, that the whole design of a satellite, as I basically shown before, it's designed this way to look at nadir. So that's how the instrument is pointed and the antennas are pointed. So we don't need to, let's say, rotate the satellites for the purposes of either of acquiring an imagery or communications, right? So this is mostly aimed into nadir, but of course there is a cone of acceptance of the satellite's movement, right? So the attitude control. So we're able to control the satellite in a certain amount of degrees, which I cannot reveal at this stage. But where the possible sessions for the data downlink will be off Nadir for the patch antennas on board. We will be using the agile attitude control with reaction wheels to point directly to the place where we want to store the data, right? So I hope that's an answer for your question.
Yes, exactly. Thank you.
Cool. Did you consider using repeat orbits since you're aiming to use a constellation? By which you mean?
Sorry, I cannot hear you well.
So could you clear out your question?
What do you mean repeat orbits? I mean, all of the orbits are repeat orbits, no?
Repeat orbit is a concept. So it's an orbit designed that way that it repeats itself, for example, 15 times over the course of, for example, 3 days. And after 3 days, it covers exactly the same ground track. So I'm asking whether you considered using something like this. So
not really at this stage, because we're mostly aimed into cover as much as Polish territory we can. So we're basically getting into our most important value is the coverage, right? And the communications is the second one. So that's how priorities are basically specified.
Okay, sure. Thank you.
So where we stopped. Yep, and that's how the coverage looks like after the simulations for 2 months and 12 months for these supposed orbits. Sorry, as we described. So on the picture, there are different colors for the numbers of axes, and this is only for nadir pointing. And I mentioned we will be available to steer the satellite, right? So what you see there, it's around on the left picture around five axes in 2 months for the southern territory, and then it's increasing due to the just one orbital plane for each of a satellite. So they are at the 54.6 inclination, which is the northwest of Poland. And these simulations have basically pushed us into dividing the first iteration of the constellation per 2 orbital planes with the different inclinations to cover it much better. So these were the initial ones. We're in the process of development, and that's how it looked like a while ago. About the service details, and this is a sum up of the presentation, and just to underline what we want to get out of the REC constellation at the 2023. So our goal is to place 8 satellites on the mid-inclined orbit to cover the Polish territory as best as we can. Keep it at around 350 kilometers, which gives us the proper GSD, but also from the other hand letting us to spend a while on orbit. rather than the orbit in the air. Imagery will be provided with 4 bands, so this is classic RGB plus near, with a single field of view of 3 per 3 kilometers, and then the following maximum image strip per orbit and daily coverage, with a certain onboard storage and downlink data rate, which has been mentioned previously. So I believe that's briefly an end of my presentation about the service details. If any questions have occurred in the meantime, I would be happy to answer them. So thank you.
Okay, thank you very much, Tomasz.